we want to evaluate the integral from minus infinity to positive infinity of cosine of sx over k squared plus x squared dx, and we know that s and k are both positive numbers. So the first thing, if we have a cosine or a sine in the denominator, okay, so above the fraction bar, we take it as the real or imaginary part of e to the ix, okay? Here we have a s inside, but it doesn't matter, so it's the real part of e to the ixs, okay? So whatever coefficient you have in the cosine of x, okay, be it cosine of 3x or whatever, you take that coefficient in the e to the ix and you put that coefficient here. Okay, so we have an s here, so we put an s. Yeah, so that is the real part of, or integral is the real part of the integral from minus infinity to positive infinity of e to the ixs over k squared plus x squared dx. So as usual, we will first find the pole, so we will set the denominator equal to 0, so we will get k squared plus x squared is equal to 0, so x is equal to plus or minus ik, and so now we can factorize our denominator, we get x minus ik times x plus ik, okay? Now we have an exponent here, so e to the ixx. So we will try to find out which way we need to take, if it's the upper half circle or the lower half circle, okay? And yes, so we will let our x be equal to r times e to the pi x theta, y we will see in a minute. And now we will take our exponent here and replace the x with this r e to the pi x theta. So we get e to the si r e to the pi x theta, okay? So the s and the I, they don't change, just the x is replaced by r e to the pi x theta. And now we use Euler's formula to convert e to the pi x theta just a minute. Wait, I don't know why there is a pi here and a pi here. There should be no pi. Sorry. Sorry, we let x be equal to r times e to the I theta. I don't know why I wrote a pi here. It makes no sense. And so we will place that x inside or e to the I x s. Okay, so we get e to the s I r e to the I theta. Okay, and now we use Euler's formula. As said, we get cosine theta plus I sine theta. And the SIR, they stay the same. And now we take the I here inside of the parenthesis. We get e to the SR times I cosine theta minus sine theta. Okay, minus because this is I squared. Okay, we have I here and then I here. So it's I squared, and so we get the negative sine theta. Okay, now if we let the radius r go toward infinity, if you want an exponential decay, so e to the minus infinity, we need our sine of theta to be positive. Why? Because we know that the e to the I cosine theta is bounded because it's something of the form e to the I theta. Okay, it's e to the I something. So there is a cosine theta here, but there is an I in front of it. So if it's e to the I something, this is bounded by definition, because we know that e to the I theta is bounded by definition. Of course, this is another theta here as here, okay? Here the theta is this cosine theta, but you don't care. Anyway, we know that e to the I theta is bounded, so about this part we don't care. We don't fear that it will expand and go toward infinity, okay? Because this is bounded. And we know that there's a negative sign here in front of the sine theta, so we know that r will go toward positive infinity because r is a radius. Okay, a radius cannot be negative. Okay, a geometrical distance cannot be negative. It's always going to be positive. And also our s, we said that our s here is always positive, so there is no fear from the s. So just we have already a negative sign here, so we just need to make sure that our sine theta is not negative, because if it is negative, we will get negative, so positive, and so if r is positive and s is also positive, you will get e to the infinity because r tends toward infinity. So we need to make sure that sine of theta is positive, and sine of theta is positive in the upper half plane, okay, because and sine is generally along the imaginary axis. So it's if the imaginary axis is positive, sine of theta is going to be positive. If the imaginary axis is negative, sine of theta is going to be negative. So here we need a positive sign. So we will need to choose the path along the upper half plane. Okay. So the half circle in the upper half plane and not in the lower half plane. Okay. So we need to choose this path. Now again, we will split our contour integral into two parts. The part along the real axis from negative to positive infinity, and the path along this upper half circle from infinity to negative infinity. Okay. And now again, we will prove that this second part, so the part along the upper half plane, vanishes as our radius gets larger and larger. So we let our x be equal to r into the pi it. Here it's correct, we have our pi. Here it was wrong, here it's correct, okay? So all these steps here that we're going to do, they come from this part here, because now we know which what path we need to choose so that at the end you get an exponential decay, and so that we can eliminate the second part, and that we are only left with the first part, and then we can use the residue theorem, because our first part is equal to our original integral, and if the second part vanishes, we get that our integral for 0, so our integral is equal to 2 pi I times the sum of the residues. That's why we proceed like that, okay? We need to get rid of the part along this upper half plane, so that we only have the part along the real axis, and then this part along the real axis is our integral, and so we set it equal to 2 pi I times the sum of the residues inside this domain, and we're done, okay? So the main point is to prove that this second path vanishes as r gets larger and larger. Okay, so we will let x be equal to r e to the pi I t. T is between 0 and 1. Dx is pi I r e to the pi I t dt. Okay, we just take the derivative with respect to t here, so this pi I comes in front. Now we replace every x with t, and every dx with dt. And so we have the integral from 0 to 1, because t is between 0 and 1. Here we have e to the s I r e to the pi I t. Okay, this s, because basically this exponent here is the same as here. It's just that, as said, instead of x, we now have r e to the pi I t, and instead of this dx here, we have this pi I r e to the pi I t dt. Okay. And so the denominator, the k doesn't change, but instead of x squared here, we have r squared e to the 2 pi I t, okay? Now we will focus on this e to the s I r e to the pi I t, because that is our potential exponential decay. Now we just need to prove that it is the case. So as before, as seen here, we will rewrite this e to the pi I t inside the exponent as cosine pi t plus I sine pi t. Now we will take this I inside, and we get so e to the sr, so the sr that don't change, times I cosine pi t minus sine pi t. Now we know that sine of pi t is positive here, first because as said, we are in the upper half plane, so sine is positive. In the lower half plane it would be negative, but in the upper half plane it's positive. And secondly, because t is between 0 and 1, also that what we decided, because t is going the e to the pi I t here will go from 0 to negative 1. And if t is between 0 and 1, it will go along the upper half circle. If t is between 0 and negative 1, if t is between 0 and 1, it will go to negative 1 through the upper half circle. If t is between 0 and negative 1, it will go through negative 1 through the lower half circle. Okay, so here we have t between 0 and 1, so we will go through the upper half circle, and thus sine of pt will also be positive. Okay, we can just plug in, for example, t is equal to a half to 1 over 2. We know that sine of pi over 2 is 1, so it's positive, okay? But sine of negative pi over 2 would be negative, for example, if t was between 0 and negative 1. But that's not the case here. We also know that e to the I cosine pi t is bounded, because there is an I here, for the same reason as before, okay? Where was it? Here. We know that this e to the I cosine pi t is bounded because there is an I here, so it's something of the form e to the I theta. Of course, not the same theta as before, but e to the I theta is bounded by definition. So we don't care about the e to the I cosine pi t. And also the SR here, I said they don't really change anything because both are positive numbers. Okay, because S is said to be a positive number here, and R is a radius, and the radius can only be positive. You cannot have negative distances, okay? So I said we don't care about this part here and this part here. We have a negative sin pi t, okay? And we know that sin pi t is positive, so the whole thing is negative. So if R goes toward infinity, we get our exponential decay as expected. Okay, we get e to the minus r, and if r gets toward infinity, we have e to the minus infinity, so 0. Okay, that's all we want, and that's why we need to choose path along the upper half circle. Okay. So now I said the second part vanishes. We just proved it through this exponential decay. And now we use the residue theorem. We know that they're counter-integral, so the part along the real axis plus the part along this upper half circle, which vanishes. So it's equal to the part 1 plus the part 2, which is equal to our original integral, so the part 1 from negative to positive infinity, plus 0, which is equal to 2 pi I times the sum of the residues, okay? And so the residues inside our domain, so inside our upper half plane, we only have x is equal to positive ik, not negative ik. Negative ik would be in the lower half plane, okay? But this is not the case here. This is not in our domain. And then we have a pole of order 1, so we can take the formula for the residues for pole of order 1, which is a lot easier than for poles greater than 1. But here it's of order 1, so we the formula is the things above the bar fraction, they don't change, and the things below it, we just take the derivative of it. So we take the derivative of k squared plus x squared, which is simply 2x if we derivate with respect to x. Okay, k is a constant. And so now we plug in our only pole inside our domain, so x is equal to ik, and so I said the things above the bar fraction don't change. So now we plug in everything, we get e to the ixs, so now x is ik, so e to the I times ik times s, okay, so e to the I squared times ks, so e to the negative 1 ks, so e to the negative ks, and below we have our 2x now, and we plug in x is equal to ik, and so we get 2ik, okay, so that is our only residue. Now I said we multiply that by 2 pi I, the 2 and the I cross out, we have pi over k times e to the minus ks, and so this is the result for our integral. But this is the integral with e to the ix, not cosine of sx, okay, e to the isx. So now we simply take the real part of it, okay, because cosine of sx is the real part of e to the isx, and so if we take the real part of it, we have the same thing because there is no imaginary part at all, and so we are still left with the pi e to the minus ks over k. Okay, that is our final result. Okay, so nothing complicated. As usual, if you have cosine of something or sine of something in above the fraction bar, so in the nominator, basically, we say that it is the real or imaginary part of e to the I something, and then we use this e to the I something because in complex analysis it's a lot easier to use e to the I theta than cosine of theta or sine theta. It's a lot easier generally. So now we solve for our poles. We find our poles, we factorize the denominator. This is not really very important, but still, you can rewrite it here. It can be useful later for critical computations, I don't know. Then you find out which path you need to take because there's a need to the I something here. There is a need to the I something here. So we need to make sure that we get an exponential decay, so e to the minus infinity. So we let our x be equal to r e to the I theta. We plug that into our exponent here, so e to the I sx. So now we replace x with r e to the I theta. We use Euler's formula, so e to the I theta is cosine theta plus I sine theta. And now we need to make sure that we get something e to the minus infinity, so e to the minus r, where r goes toward infinity. And so we see here that I cosine theta is bounded because it's in the exponent, so e to the I cosine theta is bounded. And so the only part that is important is that we have e to the minus sine theta, so sine theta needs to be positive for the whole thing to be negative, okay? I said s and r are both positive number, s is given and r is a radius cannot be negative, okay? And so sine theta needs to be positive, and we know that to be positive, sine theta needs to be in the upper half plane, because sine theta is generally along the imaginary axis, cosine along the real axis. So if you're in the upper half plane, sine theta will always be positive, okay? So now we use that path. We split it into two parts. The part along the real axis, which will be our original integrals from negative to positive infinity, and our second part that we will show that it vanishes, okay? So as said, we make all those substitutions. So x is equal to r e to the pi I t. T is between 0 and 1 because we go from 0 to -1 through the upper half circle, not through the lower half circle, which would be between t, where t would be between 0 and -1. Okay, we have our dx here. We plug in everything with t instead of x. And now we focus on the part with the exponent, so the part with the e to the isx, where x is now this r to the e pi I t, okay? And now we do the same thing as before. Here we use Euler's formula. We convert it, and then we show that given that there is a negative sign here and that sign of pi t is positive in the upper half plane, and because of and for all values of t between 0 and 1, we know that the whole thing will be negative because I said s and r are both positive numbers. And so if r goes toward infinity, we will get our exponential decay, and we will have proven that we prove that this second part goes towards 0 if r gets really big. And also, so our first part is only left. This is our original integral. So now we can use the residue theorem. So our counter integral, which is part 1 plus part 2, is equal to our original integral plus 0, and that is equal to 2 pi I times the sum of the residues, okay? Now we calculate our residue, so this is a polar form 1, so we use the formula h of x over g prime of x, j prime of x, okay, because this is a polar form 1, so everything in the denominator we take the derivative of it, and above the bar fractions we don't change anything. And now we plug in our only pole, so positive ik, because negative ik is not in the upper half plane, it is not in our domain. And now we solve and we get our residue, which is e to the minus ks over 2ik, okay? Now we multiply that with 2 pi I, and we solve it out and we get our result, and now we take the real part of it, because yeah, our original integral is cosine of sx and not e to the I sx. But because there is no imaginary part, it's the same result basically. And it also means that if we had sine of sx here, the whole thing would be 0. Which makes sense because this is a odd integral over a symmetrical interval. An odd function over a symmetrical interval, okay? Sine of sx is odd, if I say no stupid things, and it's over a symmetrical interval, so from negative to positive infinity, and so it should give 0. So that should make sense. Yes, so that's it. I hope it was clear, and yes, thanks for watching.